Okay, good morning, everyone. So we are continuing our discussion of these multi-layer perceptrons or two-layer neural networks. So this is our general picture. We have some features coming in that have dimension d. Go through a linear transform. So there's like a matrix multiply, plus we can add some intercept terms there. And then this, usually we choose this to bring us up to a higher dimension. We call these the hidden, I usually call these the scores, so hidden scores. Each of these scores individually goes through a nonlinearity. We have a choice of what these nonlinearities are. I'll talk about that in a second. And that produces these things we call activations. This is the activation function. These are the activations. And then we repeat. So we go through another linear transform. We get some output scores. Go through an output activation. And we finally get our outputs. And so what we were talking about last time is how to choose these quantities, how to choose these, how to choose some of these dimensions. So one thing we said is that we do have a choice of the number of these that we choose. If we choose too few of them, the network will be kind of weak. It won't do what we want. If we choose too many, that means we will have a lot of parameters to train, and we could run into some overfitting issues. Activations, we do have a choice, but it is really important that there is some nonlinearity here, because if these are linear, then we're going through a composition of linear operators, which it's kind of like a cascade of matrix multiplies. Then this whole thing would just be one linear operator, and you would be back down to simple logistic regression or something like that. So it's important for these to be nonlinear, but the type of nonlinearity, different ones work pretty well, and the ones that are used mainly because they're pretty simple. And then we have a question about how many outputs we want here. So this will be determined by the task, the machine learning task that we're solving. So for example, as will the choice of this. So for example, if we're doing regression and we're predicting two values, we need to have two outputs. If we're doing binary classification, we want to have one output. If we're doing k-array classification, where k is 10, we want to have 10 outputs. So that choice is fixed. And then finally, the activation function, we usually have two possibilities. Either we get rid of it completely, and we just treat these z's as the output of our network, or we go through an activation function, and then this activation also has to match the task at hand. So we'll see some examples of that in the next few slides. All right, before we move on, are there any questions about the overall structure? Okay, so, all right, so last time we talked a bit about the choices of the hidden layer activation. So one popular choice would be a sigmoid, and sigmoid goes from 0 to 1. Another choice is a variation on the sigmoid called a hyperbolic tangent, which looks just like this, but it goes from -1 to 1. So 0 would be in between. That one works a little bit better because if the inputs are centered around 0, then the outputs would be centered around 0, whereas for the sigmoid, you can see if the inputs are centered around 0, the outputs are centered around 0.5. And that doesn't work quite as well with some of the implementations out there like PyTorch and TensorFlow and so on. It works, it's just that you might get stuck in a local minimum, it might take longer to train, and so on. And another popular option is this rectified linear unit, which outputs 0 for any negative input, or for any positive input, it just outputs the input. So here again, very simple type of nonlinearity. This is the most popular choice in deep networks where you have many layers. We'll talk about why later, but it also works fine in shallow networks as well. So those are the hidden layer activations. Again, for the output layer activations, we generally have two options. One option is no activation, in which case you just output Z from the network. So let's first talk about binary classification. In this case, Z is a scalar, so we don't need to write it as a bold-faced thing. Now, if we decide to use an output activation, we want to make sure we use this sigmoid here. This is the logistic. This is, if you remember from the logistic regression, probability y equals 1 given x. This is exactly that logistic shape that we saw. Oops. You do a better job of drawing it. Okay. So this is that logistic. And now when you look at the output of the network and you get those final outputs, you know you can interpret them as a probability y equals 1 given the input way at the front of the network x. Okay. Now, for multi-class classification with k classes, first thing is we want to make sure that we use k outputs. So these should be matching. So we have a total of k outputs. Second, we don't have to use an output activation function. We could just stop the network here. But if we do want to use an output activation, we should use this softmax, which, if you remember, was the model for multinomial logistic regression, the probability that y equals class k is given by this function. And this function, if you plot it in 2 dimensions, looks like this. So those are your 2 inputs, and your output is going to be between 0 and 1. And when one of the inputs is large and the other is small, the output is high. Or if the other input is large and this is small, the output is high. So that's what that looks like. Of course, we don't typically use it with k equals 2, because with k equals 2, that's binary classification, and we can actually get away with a single output. So we tend to use this. I should actually clarify, this is with k greater than 2 classes. And in that case, it's a lot more challenging to draw this. So the pictures I drew are just drawn for interpretability. Final common task that we've seen is regression. So we might be predicting 1 target or k targets. Whether k is 1 or greater than 1, we always want to have k outputs at the end of our network, and we don't want to use any activation function, because these z's are our prediction y hat, so we don't need to do anything to them. All right, so that's the output layer activations. Any questions on these? So the next thing is to talk about the loss functions for training. So these are tightly coupled with the task and our choice of activation function. So let's start again with binary classification. And let's remember that when we studied logistic regression, we said that this is our likelihood function. Probability y equals 1 given x is this, where ZO is that last linear score output by the network. So we also know that for training, we like to do maximum likelihood or minimize the negative log likelihood. So when you take this and you do the negative log likelihood, and here we're using all our data points, I goes from 1 through n, you get exactly this expression. So we derived this back in Unit 5. So the loss is just the negative log likelihood. Now in this case, I'm writing the loss in terms of z. So that means that in the neural network, I would not be using the output of that last activation function. I would be ignoring it. I'm just using z alone, the last score. So that is one way to do it. There's another way to do it that's mathematically equivalent, where you actually use that last nonlinear activation. So again, in this case, like on the previous page, we said we want to use this logistic. So we put ZO through that to get AO. Now these are the outputs to our network. And now we can use those in this expression here. And if you plug this into here and you simplify, you do get this expression. So it's the same thing. It's just a different way of writing it. So is that clear? Both are the negative log likelihood of this. It's just that one of them is written in terms of the linear scores and the other is written in terms of these nonlinear activations. And when we talk about the implementation, PyTorch gives you these two options. You just have to make sure if you use this one, you plug in Z, and if you use this one, you plug in A. You don't want to mix those up. All right. Is that clear? Okay. So that's binary. So what about multi-class? And this is again with K greater than 2 classes. So when we studied multinomial logistic regression, we said that this was our statistical model. Probability that the label equals class K, given the original inputs X. Now we can report this in terms of these final outputs of our network, the linear score outputs. And again, if you take the negative log likelihood and this is over your full data set, you get this expression, which we derived back in Unit 5. So this is what we use for training. We minimize this loss in order to maximize the likelihood. We call this cross entropy. This one we call binary cross entropy. Again, if you do it this way, you're using the linear scores coming out of the end of the network. You're ignoring any activation at the very end of the network. If you would like to do this activation at the end of the network, you can. You just want to make sure you use this same function here. That will give you these output activations, and then you can plug those into this expression. This is the negative log likelihood written in terms of these output activations. So this is another option. Yeah?
So what exactly is the point of doing the output activation if we're not necessarily at our minimum yet? It seems like it just add more calculations.
Yeah, I would agree with you. It's certainly not necessary. We did use it back in our example in order to make this plot. We wanted to convert those scores into a probability between 0 and 1. And we did that by putting it through that activation. So we can make the plot.
Help with like interpretability.
Interpretability, yeah, that could be one motivation. But yeah, personally, I would recommend just not having that in the neural network unless you really want to make a plot like this. I think it's a little bit easier. And in fact, if you read some discussions about this online, people say that there are some numerical differences between these options just due to numerical precision issues. And apparently, I believe that this one is a little bit more accurate than this one. It's a little bit less sensitive to numerical round-off issues. So that would be another reason to use this. But probably either one you use is going to work fine in most implementations. All right, so that's binary multi-class classification. Any questions on? Yes?
Can we say logistic regression is the special case of neural network without hidden layer?
Yes, exactly. If you think about this and then you take away this part, then you just have logistic regression. Exactly. Multinomial logistic regression here if we use this softmax. Exactly. So basically, the way we're thinking about this is a feature transformation, a nonlinear feature transformation that makes our features more linearly separable so that this linear regression works. And when we did SVM, we built the nonlinear transformation implicitly through a kernel, but we only have a few kernels to choose from, and it's not clear which is the right one and whether any of them are really suited to any given data set. So here, the philosophy is let's learn the transformation ourselves and make it custom to our data set. So this is, I would say, a more powerful method. All right. Good questions. Any other questions so far? Okay, so the last question then, what kind of loss function do we use for training regression? Well, if we think of the likelihood model as, I should write here, this is IID Gaussian noise. So it's like saying that y equals z out plus epsilon, where epsilon is IID Gaussian. If that's our model, then our likelihood is this Gaussian here, and the negative log likelihood we know is this quadratic, or RSS. So basically, this is the most common option. It is possible to use other models. If you had maybe a non-Gaussian noise, then you would have a different distribution here, and you would get something different here. The most popular one that's used a lot for images is you put absolute values here, get rid of the square. So you use L1 loss, and that's sometimes works a little bit better for images. And you could say that that would be equivalent to assuming Laplacian additive noise here, if you wanted to interpret it statistically. Okay, so that's how we choose the loss functions. As you can see, they're very tightly connected with the output layer activations if you choose to use one. And those are the main things in terms of choosing the designs of this. Now there's a few other choices that we'll talk about when we talk about optimization. We have to choose some parameters for the optimization algorithm, but we'll get to those later. But in terms of the architecture, I think we've discussed all the different choices now. There are many other activation functions beyond the few that I listed. Some of them are very, specific. You would want to use in a particular situation. You can read about them on your own. We'll talk more about some of them in the next unit. And in the next unit, we'll talk about modification of these that are convolutional. So it's doing a convolution rather than a matrix multiply. We'll talk about that in the future too. Both would be linear, but that would be a constrained class of linear transforms. All right, any other questions on architecture? Yes?
Yeah, so can we have the nonlinear transformation in the hidden layer if we don't do the linear transformation?
So,
Yeah,
So-
I mean, this is the activation part. So
Uh-huh.
can we just have some like nonlinear transformation in the very beginning?
oh, right here?
Yeah.
You could, I would say, people would think about that more as a standardization, or like a standardization would be, you could just say a shift in a scale of your original features, right? So we could think about that. That's not nonlinear. Sometimes with some data sets, you might do something like remove outliers. So you might, like any value that's beyond a certain, you just clip it. And that would be a nonlinear transformation. But again, you would probably apply that to the whole data set rather than putting it as part of your neural network. So when we talk about image processing, there are things that we do here to artificially enlarge the data set called data augmentation. So you might take images and you might shift them and stretch them and change the colors. So those would be transforms of this that they're not implemented as part of the architecture, but they're implemented when you train as like an extra step in the training process. But beyond that, I don't really see people putting in activation functions here. Because, yeah, I think generally speaking, the first thing you want to do is this linear, and then, yeah, that's just how we tend to build them. Okay. All right, any other questions? Okay, great. So now let's talk a little bit more about how we train these. So as we learned in Unit 6, we would like to define an optimization problem, minimizing the loss, and then we're going to use our favorite algorithm to do this, gradient descent. So let's talk about a little bit of notation. So the overall loss, I'm going to use a script J, and this script J, you can see, is going to be the average over all my training samples of the per training sample loss, which is going to be a non-script J. Okay, so this one is for the ith training sample. This is the average over all the training samples. So when we do gradient descent, we have this. So we say that the new parameters equal the current parameters minus a step size that can change with the iterations or not, but this needs to be a small positive step size, times the gradient of the full cost evaluated at the current parameters. And so we can plug this expression in here, and because gradient is linear, we can pass the gradient through there, and we can get this expression where we see here, this is the gradient on the ith sample, and then we're averaging all of those and multiplying them by the step size, negating so that we're going downhill rather than uphill, and so on. So that would be the sort of overarching approach. But when you look at this, you're noticing that each iteration of this algorithm computes n gradients, n of these. And it's often the case in these neural network problems that and the number of training samples is very large. It could be like 1 million or something. And that means that you're doing 1 million gradients just to even take the first step. And that might not be very efficient. Because as we know with gradient descent, the first step might not even be taking you, in the direction towards the minimum. You might be taking some curved path. And so you spent all this effort really focusing all this computation on taking this step that's not even in the right direction. So can we reduce this smaller? Can we change the algorithm? That leads us to what we call stochastic gradient descent and the concept of mini batches. So here's the idea, is that in each gradient descent step, instead of using all the different samples, we're going to select a random set of samples from our training data. We'll call that a mini batch. And we'll evaluate our gradient only on that mini batch. And in the next step, we'll choose another mini batch and work on that mini batch. So that way, instead of using all the samples, we're just using a random subset at every iteration. That's the main idea. So here's some of the details then. So this is sort of a visualization of all the training samples. Maybe there's 50,000 in MNIST. And a mini batch, typical size might be on the order of 100. So really a huge difference between using all and using a mini batch. Now, what we'd like to do is use a random set of samples. And so one way to do that is to shuffle the entire training data set. And then once it's shuffled, then I can take contiguous chunks out of the shuffled one. So let me write in here full batch of shuffled training records. Okay, so these are randomly ordered, and then I can take the first, and then once I'm done with that, I take the second and the third, and so on. Okay, so here's a little bit more of an algorithmic description. At every step t, so a step is going to be one of our gradient descent updates. We're going to randomly select a subset of indices. We'll call that index set I sub t because it's going to change with every step. We're going to compute the approximate gradient. And it's approximate because we're averaging over just that subset of indices. So this absolute value of the subset, that is the size of the subset, the number of samples that we're using. So this is just a regular sample average. And this is, of course, the gradient evaluated at the indices in the subset. So we're going to call this the gradient G at iteration t. And then this is our gradient descent. Step size, gradient. So the reason we call this stochastic gradient descent is because you can think of G as a random approximation to the full gradient, this one. And it's random because the subset of indices is random. So that means that if the gradient is pointing in a certain direction, this approximate gradient is pointing kind of in that direction, but it's a little bit in some other direction. And that kind of deviation from the true gradient direction, you can think of it as random. Question?
So when you say training records, do you just mean the data, like the X, Y pairs?
Yes, sorry. That would be clear. So this just means the full batch of training data. Okay. And we, instead of here, we write samples. Okay. Is this idea that stochastic gradient descent, main idea making sense? All right. So why does this work? It works because the gradient approximation G is correct on average. So how can we make this formal? If you look at the expected value of G for a fixed theta t, these are the parameters at time t, it reduces back to the full exact gradient. So the rationale there is, if you think about what's the probability that I use any particular sample in my data set here, the probability is the same for all samples, right? So when I take this expectation, I'm taking an expectation over this random subset IT, and all the samples are equally likely to fall into there, so I just get the full average gradient over all the n samples in my data set. Okay, so the average value of our approximation is the truth. You could say it's unbiased. This is an unbiased approximation of the gradient. Okay, and for that reason, if the gradient is unbiased, then so is the new update theta t plus 1. To see that, we just take the expression, plug that into here for this, and then we apply linearity of the gradient. So expected value of theta t given theta t is just theta t itself. And then for the second term, we can pull out the alpha, and we look at the expected value of gt given theta t. We know that this is this. So on average, the stochastic gradient update is exactly the same as the full gradient update. So you could say this is also unbiased. But that doesn't mean that at every instance it's the same. It's always going to be a little bit different. It's just that the direction it's off is it's kind of like, you could say the gradient noise, which is the difference between, so let's call this gradient noise epsilon. This is the difference between the true and approximated gradients. You could say that this is a zero mean random vector. So we're saying that the approximated gradient is the true one plus some noise, and according to this, that noise must be zero mean. So the trajectory, or the set of thetas that you get, is more noisy than the true one. So the true one might smoothly go towards the optimum, and this one is like jumping around. It's going in the right direction, it's just jumping around as it gets there. Maybe I'll draw a little picture. So we have these are the cost contours. We start somewhere here, the true gradient descent smoothly goes there. Stochastic gradient descent just kind of jumps around on its way to getting there. So because it's jumping around, and in fact, once it gets to the bottom, true gradient would stop at the bottom, whereas this stochastic one might keep jumping around. So to counteract that, we'd like to reduce the step size. If we reduce the step size alpha, you can think of that as like you're doing more averaging as you evolve your trajectory, and what that will do is it will cut down on these variations, and they'll get much smaller, and it will take you more steps to get here, but you'll be closer to the true trajectory. And remember that one full gradient descent step is very expensive because it has to use many gradients. One stochastic gradient descent step is very cheap because it's just using a few. So even though you would say stochastic gradient descent with a smaller step size will take more updates to get to the bottom, each of those updates is much faster. So in terms of total computation time, It's usually the case that stochastic gradient descent is much more effective. It converges with much less computation to the minimum. Okay, but it is the case that as your batch size decreases, things get more noisy, and you should correspondingly decrease your step size together. So smaller batch size, smaller step size, and then you'll get decent performance.
Is there any rule of thumb to how big your batch size would be relative to your sample size? Or is that a design parameter if they kind of mess around with it?
It often the batch size often has to do with the amount of memory that you have in RAM. So in particular, when you start working with these challenging problems, you're using a GPU, and the GPU has a certain amount of RAM. Maybe it has 8 gigabytes or 16 or 32 or something, and each image is going to be a certain size. So the question is, how many images can you fit into that RAM? And so that will place an upper limit. Still, you might find some experimentation is handy. The choice of batch size and step size will affect whether you get stuck in a local minimum or not. So it's a bit of is more of an art than a science, I would say, in terms of choosing that. And if you have a lot of computation power available, you just set up some very large search where you try all these different batch sizes, all these different step sizes, and you run all these experiments for like a week until you figure out what was the best combination. Or and if you're at a place like Google or something, and you have just massive computation available, like this is essentially what they do. They just do this in parallel, and but that's essentially the state of it. Question?
Is the variance of GT biased?
I guess we're not computing the variance. So what's your motivation for asking?
Because I think smaller batch maybe they may have higher bias or variance. I don't know.
So the variance will increase as your batch decreases. There's more noise. Yes, right. So that's what I was saying here is that as your batch size decreases, you expect a more noisy trajectory, and then you reduce the step size to counteract that. By reducing the step size, it's like you're doing more averaging. Because you can see here like the new update, if alpha t is very small, that means you're using a very small scaling of this to change this. So you make a very small adjustment, and that means a very small change, and so it takes you many steps, many new gradients to make a big change here, and that averaging across those many gradients reduces the variance. So this is why we tend to decrease alpha as the batch size decreases to reduce that variance. And that way we have a reasonable amount of jitter here, and when we get to the bottom, we don't bounce around the bottom so much. We reduce our step size so that we actually converge to the bottom and stay there. Yeah, we'll talk about this much more in the next unit. There's in fact schedules, many different schedules that are popular. The most basic one is you start with a relatively large step size, and then as you go, you decrease it, and so that once you're found a good minimum, you use a very small step size so that you don't bounce around much, you just stay there. But you use a large step size at the beginning in the hope that you make fast progress and that you jump out of bad local minima. So these schedules, we'll talk about those in the next unit. But for now, just imagine this is a fixed value across T. That's probably enough for the discussion right now. Any other questions? Okay, so here's just a little bit of terminology and details on the implementation. So as always, let's say that we have n samples in our training set. And let's say that we have b samples in each mini batch. And these are mini batches that are, it's a partition of the data. So we will never use the same sample in more than one mini batch. Okay, so if that's the case, then the total number of mini batches we need to cover our data set is T, capital T, which is n over b. Okay, so that means if I do T, okay, so I'm going to do one stochastic gradient descent update per mini batch. And after I do T updates, I will have passed through all of my training data once. I will have used every training point once and only once. So we call that the training epoch or epoch. An epoch, a training epoch goes through the entire training data once. So this is the meaning of an epoch. One pass through your full data. Typically, you need many epochs, maybe tens or hundreds, typically. But you may have many mini batches in each epoch. So the total number of updates you have is T times the number of epochs. Okay, so that's how we set this up. And so the way we implement this is at the beginning of every epoch, we randomly shuffle all of our training data. And then we fix it for that epoch, and we partition those shuffled indices into T contiguous, non-overlapping subsets. So like we showed here. So you have one, and then the next time another, and then the next time another, and so on. So we get these T different non-overlapping contiguous subsets, and each of those index sets defines the mini batch used at gradient descent update step T. And because of this random shuffling, every epoch we have different subsets of mini batches. So we don't want to use the same set of indices over and over again. We want to randomize that. Okay. Is it making sense? So this is how we tend to do our optimization. All right, so there's two more things to talk about in this unit. We want to talk about how we compute gradients. That's the one remaining thing on the theory side. And then we want to talk about how we implement all of this in Python. So let's see, we have 10 minutes left today. We won't be able to cover either of those. Let's skip ahead, and we'll talk about the computing gradients first. This is back propagation. So we'll talk about this today for the next 10 minutes, and then we'll come back and we'll start again on Monday. I think because there are a few complexities here, and it won't hurt to see them twice. Okay. So again, this is what we just discussed. This is our mini batch stochastic gradient descent update. So here we see the new parameters equal the old ones minus step size times the average of our gradient. And here what I did is I moved the gradient to the other side of the sum so that we could define this as the mini batch cost. So this is the cost per sample summed over all the samples in the mini batch, and we're going to now put a little superscript t here because you can see that this cost will change with every t because I'm going to use a different subset for that t. And of course, it's also a function of the parameters at that update t, so there's a theta t there. Okay, so the whole question though is how do we compute this? This is complicated because our network has multiple stages and some of the parameters are buried in these different stages. So we need an organized, systematic way to figure out all these gradients. And so in particular, at the tth iteration, we need to compute the partial derivative of that mini batch cost with respect to the hidden layer weights. And remember, this is a whole matrix of weights. So this matrix has two indices, L and J. We also have the partial derivative of this with respect to the hidden layer activations, and this is a vector. So we have a bunch of indices to compute there. Then we have the output layer weights and the output layer activations. So these are all the things we need to compute in our two-layer neural network. So that's what we're going to study, is how to do that. And just to make the notation a little bit cleaner, we're going to drop this batch index t from now on. We're not going to have a t there, because we're just focusing on one t, and so we can forget about the t for a moment. Okay, so this is how we're going to organize our computations. We're going to visualize everything according to this picture here, which is called the computation graph. So this is just a picture of how the different variables come together in different stages to create new variables. So for example, on the left, so the data flows, we can actually think, let's think about from left to right. So we take in our features, and we actually have a whole batch of these features. That's why there's some curly braces and I there. So we take in the features from the mini batch. We also have, let's say, some particular hidden weights and intercept terms, and we know that together these things determine our hidden layer scores, right? And then this is the equation in particular. So we take the features times this matrix here, add this vector to give hidden layer scores, and then we do this for all the elements in the batch. So that's how these two things give us this. The next thing is these hidden layer scores go through an activation function to give us those activations. And so the equation for that is this. So this is some element-wise function that looks at a given element here to give us this element over here. And this happens for all the elements in the batch as well. The next stage is we take these activations and these output layer parameters, and we do this linear stage to get here, and that is described by this. So we multiply those activations by this matrix WO. We add the bias, or intercepts BO, and we get the scores ZO. And the final thing we do is we want to compute the loss. So to compute the loss, we have to take the outputs of our network. Now notice we are not using any output activation. We're just using the Z's. That's all we need. But we also do need to bring in the training targets. So the loss is those Z's and the targets. And of course, we're summing over all the different elements in our batch. And that's going to give us one scalar value here. So this is, if you think about how data flows through the network, it goes from left to right this way. And this is what we call the forward pass. Forward pass is exactly this sequence of operations. Now to compute the gradients, we're actually going to do a backwards pass, and that's what we're going to describe next. And as I mentioned, the loss is written in terms of Z, not A, just to simplify things, but we could have put in some variables A, we could have had an output layer activation, and in that case we would have had to define our loss differently, but this is just simpler to describe. And I'm using some color coding here just to distinguish the variables. So the observed variables are data. These are the green ones. The trainable ones, the ones we have to figure out the gradients with respect to, those are the blue ones. And then all these purple ones are a result of combining the observed ones and the trainable ones. Okay. Great. So to move forward, let's review the chain rule, because as we'll see, the chain rule is going to guide everything about our computations. Let's start with the simplest case of scalar variables x, y, z. So here again, we have a computation graph, which means z is a function of y, and y is a function of x. So that's what we have here. So this is the graph, and what I want to do, let's say, is compute the derivative of z with respect to x. The chain rule says I can do that by dz dy, dy dx. So I can do that in 2 stages. Now here's an interesting thing. Imagine that there's actually some other intermediate variable between y and z. So perhaps I could have drawn my computation graph instead like this with another variable. So there's a couple choices. I could do this dz dx as a product of dz du, du dy, dy dx. I could do that. But let's say that I have previously computed dz dy. I can also use that in place of this product. And at that point, I'm right back to this graph here. I'm just basically saying, this u is not helping me. It's there. I'm just going to treat it as some, I guess you could say, a hidden variable. And I'm going to focus on dz dy, dy dx. That's an option. And when you have a very deep graph, like you can see why you don't necessarily want to do all this over and over again. Maybe you've already figured this out. And if you know that, then you can get dz dx if you want by reusing this computation that you already computed and adding one more. So that's sort of an important point. It's kind of obvious when you think about it, but it is important. So you don't have to use every step in the graph if you don't want to. The last thing is that if I have a graph where there are several intermediate variables at some node, and another way that we could draw this perhaps is this. But the point is, even if I draw it the original way, the point is that these curly braces tell me that there's actually several here in the middle. Then, when I compute the chain rule, what I have to do is I have to worry about all the different paths through the network, and I do that with this summation. So here's where we use our multivariate chain rule. So dz dx, again, I'm going to kind of forget about this. I'm going to do dz dy dx, but I'm going to do that for each of those different paths, and I'm going to add them together. Okay, so again, whenever you see, maybe it's even better if I leave this out. Whenever you see this graph, and you see that one of the nodes actually has several variables there, just remember that if you want to pass through that node using the chain rule, then you have to do this multivariate chain rule and take into account all those different variables in there. Okay, so basically, with that as the background, we can think about how we will do backpropagation, or how we will learn all the gradients in this simple computation graph. And by simple, I mean that we're going to look first at the simple case where we have scalar variables, so no vectors anywhere, and a batch size b equals 1. So that means there's only one scalar at every node. We're going to do this first, just because this is easy. And once we understand this, then we'll make things harder. We'll add multiple things, and then we'll make things even harder, and we'll add vectors. And that's the actual thing that we care about. So we're just going to start easy. So the first thing is the forward pass. So here's the forward pass written out in this simple variable case. Everything's scalars. And now, how do we do gradients? We're going to do backwards computations. We're going to start at the end and move our way left. And it goes like this. First, we're going to compute the gradient with respect to the different variables on the top row. So we'll start dj dzo. Okay, that's what we want to compute first. To figure out how to do that, we have to look up the equation that relates script j to zo. That's this equation. You can see that involves this lowercase or non-script j. So dj dzo is just what I'll call j prime, the derivative of this function evaluated at zo. Okay. And now notice that in order to actually compute this, I need to know the value of zo. And that's what I got in the forward pass. The forward pass gave me that variable. If I didn't do the forward pass, I wouldn't actually know this quantity and I would be stuck. So that's why we have to do the forward pass first, just to get all the variables. And then once we have them, we can evaluate our gradients using those variables. Okay, so that's dz/do. Next one, dj dzo. dj daa hidden, this one. So to do this, this is my little computation graph here. So I'm going to do dj dzo, dzo dah. Here we are. So this first term, dj dzo, that's something I've already computed. So I don't need to compute it anymore. I can just plug that right in. The new thing I have to compute is dzo dah. To do this, I have to go find the right equation. And now you can see that dzo dah, that's pretty easy. That's just wo. And so those are now computed. I multiply those together and I have this. Next thing is dj dzh. So I can do that. dj dah, dah dzh. So I'm skipping over the zo because it's not helpful. And this dj dah, I already computed that. So I have that. That's done. The next thing I have to do here is just dah dzh. So here again, I find the right equation. And so dah dzh, I just take the derivative of this function and I evaluate that derivative here. So I'll call that derivative h prime. Okay. So now I have all the gradients in the top row. Now I'm ready to solve for the gradients of the parameters. So the first one is dj dbo. So I use this computation subgraph, and I do dj dzo, dzo dbo. I've already computed this, so that's done. Now I just need to look at dzo dbo. So I come over here, and I see that that derivative is just 1. So that's easy. So now I know dj dbo. dj dwo, I do this. So dj dzo times dzo dwo. I know the first part. The second part, let's look at the equation. dzo dwo is just ah, so that's what that is. Now I know this. Again, the key point is I'm reusing this quantity that I computed earlier a couple times. And the last step is dj dbh. So we can think of this subgraph like this. So I just do dj dzh and then dzh dbh like this. But this dj dzh is something that I already computed, so I can use that. And then I just have to figure out dzh dbh. But for that, I have this equation. You can see that's just 1. Okay, so then the very last thing is dj dwh is dj dzh, dzh dwh, And for the very last one, DZHDWH is just X. So by moving my way systematically backwards, I compute all the gradients with respect to the parameters. And now I have what I need to compute that gradient descent update of those parameters. And then with the new parameters, I start all over again. I have new parameters, so I need to recompute the forward paths to get new intermediate variables. And once I have those, I can begin my backwards pass, and I can get gradients with respect to those. And then I repeat this for every mini batch. Finally, I come to the end of my epoch, I reshuffle, and I do this again. Okay, so that's enough for today. Next time we'll review this, and then we'll also go through and make it a little bit more challenging. All right, have a great weekend, everyone.